Hello everyone, welcome to my AAT Tech Talk. Today's my topic is implementing pre interpretations in pipeline RlSC process. So this is my topic. Let's understand more about this topic. Pipelining is an important implementation technique that exploits the parallelism among instructions. Impress interruption problems arise when a pipeline processor has a multiple cycle uh, functional units because instruction completion might be out of order. An early issued long-running instruction might generate an interruption after the completion of several short-running instructions issued later, resulting in an impressive instruction. Here we investigate from an WI implementation of point of view. For solution to the interruption problem in a pipeline, the reduced instruction set computer processor having multiple functional units. Pipeline computer architectures offer significant performance benefits over the traditional sequential model of computation. In a sequential model, where processing of the given instruction does not begin until all previous instructions are finished. Only one instruction is active in the processor at a given time. But in a pipeline computer, different instructions can be in different stages of the pipeline line simultaneously. So pipeline is an implementation technique that exploits the parallelism among the instructions in a sequential instruction team. The processing of instructions in a pipeline machine breaks down into distinct stages. Ideally, n instructions that can be simultaneously active in the processor at a given time, one in each of the n pipelines given a theoretical speed up of n over the sequential model. Here, often instruction exits the pipeline determines the through throughout of a pipeline processor because the pipeline stages are hooked together. All the stages must ready at the same time. Must ready at the same time. The time required to move an instruction from current state to next stage is the machine cycle that is determined by the time required for the slowest pipeline stage. Four purposes are here. We assume that one machine cycle equals to one clock cycle. For simple instructions, all pipeline stages of 10th require one machine cycle. However, complex instructions such as multiply and divide operations, it is impractical to require or that all complex instructions complete in one machine cycle in the execution state. And a practical approach is to implement multiple multi-cycle functional units, so that the processor can issue a complex instruction to a functional unit specially reserved for this operation. While this function is being executed, other functional units can execute other short instructions that immediately follow the complex instruction. And the simple instruction then will update the contents of the register before the complex instruction does. It for some reason the complex instruction causes an exception during its execution. For example, a dividing by zero of or a memory exception error, the register file will not agree that of the sequential execution mode. An instruction set that issued after the instruction would which would not complete because the exception condition has modified the register file, thus cause thus causing the lack of agreement. Therefore, the stage of processor at the time it is issued, the complex instruction cannot be reconstructed, and the program cannot proceed 1% without corrupting part of the register file. This type of interruption. In a press interruption, the state of processor is consistent with that of the sequential model, and the sequential model of the same processor. Designers have two main techniques at their disposal for solving the solving out of the order completion problem, and for providing precise interruptions in a pipeline processor having multiple functional units. First, they can always keep the state of the processor precise and precise by allowing the instructions to update the register file in order only in the order or in which the program issues them. Second, designers can allow the state of processor to become impressed, but they will must provide a procedure to recover the precise state of the processor in the event of interruption. So in this picture, you can see the processor instruction set, how the processor will work, and what are the instructions will be given into that processor. So you can see here LDB means load register one, and here OP means the uh, output opcode. Sorry, here LDW means load word immediate. So here the words will be loaded, and these are the store words, and these are the some conditions to which are given into the processor instruction set. Here we compare four methods of providing precise precise instructions with regard to the performance degradation and cost implementation from the VLSI silicon resource perspective. Our results provide the valuable information of VLSI processor designers to consider if they include the precise interruptions in their designs. There are these four methods are in circular instruction completion, recorder, buffer, histophile, and futurephile. This is the following flowchart which executes the pipeline, which is the pipeline stages of the model architecture: instruction fetch, instruction decode, register fetch, memory access, execution, write back. This is the pipeline stages of the model architecture. So we will know the what is meant by the architecture model. To describe the various models, we have chosen a model architecture with the following features. A load store reducer instruction set, an easy decoded instruction set having 21 total out of 15 instructions as shown in the box. A four stage pipeline: instruction fetch, instruction decode, register fetch, execution, memory access, and write back. A register file with 16 16-bit registers. A processor with a 16-bit address bus and a 16-bit data, three non-pipeline functional unit, arithmetic logic, integer multiply divide, memory access, and the floating instructions, which are not considered, which are not considered. The pipeline structure, the pipeline structure of the model architecture used in this research is modified version of a popular load store reduced instruction set computer called D The explanation X2 figure 1 shows the pipeline structure of the model architecture. So here is the execution state of our model architecture that has three functional units. ALU means arithmetic logic unit, uh, integer multiply and divide memory access. This ALU execute an integer or add, integer subtract and branch instructions. The second unit executes the integer multiply and divide instructions. The memory access unit executes the load and store instructions. We assume that the instruction add, subtract logic operations executed in ALU takes one clock cycle. Memory access takes two clock cycles, and the integer multiply and divide operation takes 8 clock cycles. In addition of four pipeline stages, our model architecture uses the following units. Register control, buffer control, register write back and instruction scheduling. Register bus multiplexer feeds the data from the appropriate functional units to the register file and to the data multiplexer if necessary. The data multiplexer feeds the data from the register file, the instruction decode unit, or the result bus multiplexer to the functional units. Register file working registers and the pipeline registers buffer between pipeline stages and the bypass path feeds data from the result bus multiplexer to the data bus multiplexer. In this picture, you can see the function flowchart or the instruction set diagram, block diagram for the pipeline RlSC processor with multiple functional units. Here you can see this, which are mentioned in this previous slides: instruction fetch, instruction decode, data multiplexer, and these are the arithmetic logic units and the memory access, and these are the arithmetic operations which are done on the data. All this results into the result bus multiplexer, and it directly passes into the register file. And next, the bypass path will directly be directed to the data multiplexer again, and this register file also directed to the data multiplexer. This table one is a list of subunits used in the result control buffer units for various architectures. Method: original, imprecise, subunit, result shift. Result shift register 4-bit per entry. In order completion, result shift register 20 bits per entry. So these are the bitwise entry for the different methods or on different files which are discussed in the previous slides. So figure 2 presents the detailed block diagram of the processor. All versions of the model architectures used in the result control buffer to provide impress precise instructions. A model includes a bypass path to solve the data hazard. The detailed structure of the result control buffer unit varies from one method to another. Table 1 shows the subunits needed for the result control buffer buffer unit with different methods. From table 1, we can see that the all methods use in the shift register, which provides appropriate control signals to all pipeline stages and the functional units. When the processor decodes an instruction, it examines the contents of the result shift register. For an instruction that requires n cycles for execution, the processor makes an entry for this instruction in stage n of the result shift register. If the stage is available, otherwise the processor holds the instruction until the stage becomes vacant. On every clock cycle, the control information in result shift register shifts from each stage to the next lower stage. When control information for a given instruction leaves stage 1 of the result shift register, that instruction has completed in execution. So these are all the points we discussed in the explanation for the previous slides. So this is as a program issues an instruction that requires the clock cycles to execute the processor reserve state in as well as n minus 1 stages through one of the result shift register. This precaution prevents the program from issuing second instruction until it knows the second instruction will finish after this first instruction. Figure 4 shows the operation of the result shift register for a simple program using the in order completion method. This approach conceptually simple and requires the little logic to implement. It does not, however, make a useful of multiple functional units. The processor puts some of the functional units into an ideally state to avoid out of order instruction completion. The program may sometimes hold a simple fast instruction even though they are not hazardous in the pipeline, and this is the major disadvantage of this method. So in this figure 3, it shows the result shift register operations on A and recorder buffer operations. In this figure 4, it shows the result examples for in completion method and the clock cycle speed of calculations which are the given in this table. The figure 5 presents the operations on the result shift register for a simple program using the recorded buffer method. It shows that short instruction sub IDW add issued after the long instruction multiplexer finish earlier than the long instruction. Recorder buffer uh, takes from the form of circular queue. When the processor, i- processor issues an instruction, it places the current program counter and pointer to the destination register in the recorder buffer entry that the tail pointer points to. It detects an exception. It stops a issue in the preparation of further interruption and inhibits all further writes into the register. After the processor updates the register file, it is history file method. This is all examples and basic information about the history file method. In history file method, the processor maintains a recorder buffer but uses it differently than in the recorder buffer method. This is another method, future file method. The future file method differs from the history method in that it creates two register files, one called architecture file and other called the future file. The history file creates only the working register and the architecture. The future file, like the history for buffer method, allows the instructions to complete any immediately upon the completion of an instruction. Then provides input data to succeeding instructions. This is the performance evaluation. You can see it, and as for achieving the precise interruptions at high-speed computation, the history file method should be used. For achieving better cost performance ratio, VLSI power processor the should use the in order completion method to provide precise interruptions. Many high-performance workstations have several processors running simultaneously. Consequently, we are currently investigating the cost and performance issues involved in the implementing precise instruction on a multi-processor system. So this is a presentation about, and I hope you understand this topic. Thank you.